Well, that's a very difficult question. We have one example of life to extrapolate from, so we are really stuffed, let's face it. If you look at the habitable zone around our Sun, it extends from the orbit of just outside the orbit of Venus to beyond the orbit of Mars. Now Mars appears to be a pretty dead world. Venus, which is just kind of slightly outside the habitable zone, also appears to be a dead world. So only one of those three has life, and we don't know why the Earth, why everything was special on Earth. I mean, on Mars, for instance, you know, it hasn't really got much of an atmosphere. That was stripped away by the solar wind. It was a small planet, so it cooled down very quickly, lost its internal heat. Venus was slightly too close to the Sun, so its water, we believe it had oceans, was boiled off into space, and it now has a runaway greenhouse effect. But we don't know what was so special about the location of the Earth. Complexity has stalled on all the other planets. There isn't even plate tectonics on Venus, but not only is there plate tectonics on the Earth, complexity has continued to increase. You know, there's been the evolution of life, the evolution of technology, the internet just continues to increase, and I don't know, we don't know what the factors are that have made that possible. I would design a telescope that could actually image a second Earth, because I'm not sure I'm going to be able to see that in my lifetime. At the moment, pretty much all the planets that have been discovered indirectly. I mean, when the Earth goes around the Sun, it tugs on the Sun, and the Sun tugs on the Earth, but the Earth has a small tug on the Sun. And this is the way in which we've detected planets around other stars. We've looked at a star and we've seen it tug slightly one way, tug slightly the other way, and we've inferred the existence of planets. We will probably be able to detect on a planet that we find maybe the existence of oxygen, methane, which are biological gases, but we're a long way from imaging a planet. The principal problem is that the central star is many billions of times brighter than the planet, so we need a way of screening out the star, and then we would need a very large telescope. But we've got two problems. You've got to pick up the light of a very faint object next to a very bright object, so you've got to screen that out. But there isn't much light that's given out by a planet, it's only reflected from a star, so you've got to collect a lot of light. The way we look for faint objects is we build bigger and bigger telescopes. They're light buckets, so we build a big bucket that can detect more. The bigger telescope is also able to see finer detail, so we will certainly need a much bigger telescope. But I think that the size of the telescope will be so huge that it can't be a monolithic one. We will have to fly bits of it, maybe millions of miles apart, and we'll have to detect the light on these bits, maybe thousands of them flying in space, maybe in formation. LISA, which is a gravitational wave detector, is I think scheduled for launch in about 2015, and that will actually use a fleet of about 4 or 5 probes, which will have to maintain an exactly precise distance at all times. So it's a major problem. But I mean, the payoff is to find a second biology. I mean, that is just fantastic. The very large telescope, the extremely large telescope, the ever so big telescope. I mean, where the hell do you go? I was very impressed a few years ago because at Cambridge they made the very small array, and I thought that was good. This was an array of very small radio dishes to look at the cosmic background radiation, which is the afterglow of the Big Bang, which permeates the universe, and they only needed small telescopes. I just love the idea that you'd put all these small telescopes around, and really they just cover the area of a dinner table, and they call it a very small array.